Hello, calculus students. Today's lesson is focusing on what is an asymptote and how do you calculate them. Before we learn about asymptotes, though, we're going to start off with this warm-up. So go ahead and take a few minutes, try this warm-up on your own, and then come back and see what we got. So here's what I got. Woohoo! In problem part A, I just factored. When I factored, I saw that a common factor in the numerator and denominator was x minus 2. So since it is a factored, it forms a 1 when you divide, and I can cancel them out. And I'm left with x plus 2 divided by x minus 3. In the other problem, I decided to multiply by the reciprocal since the denominator was just a single fraction, so I'm able to multiply by the reciprocal in this case. One important step to do when you multiply by the reciprocal is make sure you multiply times everything in the numerator. So you distribute that in, and I ended up with x plus 2x squared. And hopefully so did you. So now we're going to review the definition of an asymptote. Oh, by the way, I feel like I should address my NASCAR headphones. I feel like it makes me look like I'm a race car driver. Hopefully the audio is good. Okay, so the definition of an asymptote is a line such that the distance between the line and curve gets closer to 0 as the x or y coordinate goes to infinity. That's probably a more detailed definition than you've heard before. Maybe in pre-calc or algebra 2 you were told an asymptote is a line that the function gets really, really close to and never touches, which is basically true, but you can see in this example right at the top, the curve is definitely touching the asymptote line, and that's because curves are allowed to cross the asymptote line. The main thing is that the curve is getting closer and closer into it, okay? So that's why I say the distance between the line and the curve gets closer to 0. It's just saying it's getting closer and closer. So that is like the official definition of an asymptote. And then we've got the 3 types that you can see below. So the first type that we can see, this is a vertical asymptote. Vertical asymptote. And so the formal definition of a vertical asymptote is as x approaches some constant c from either side, either the left or the right, then the curve is going to infinity, and it can go up to positive infinity or down to negative infinity. Then the definition of a horizontal asymptote is as x goes to infinity, so x is now going to positive or negative infinity, then the curve approaches some constant b. So b is a horizontal line, and the curve is just getting really close to b. And then this last one is less common. We call this a slant asymptote. For the purposes of our class, we're not going to talk about these as much, but I just want you to be familiar and recognize it when you go to college. So a slant asymptote you can see is like more on a diagonal. It's not horizontal or vertical, but it's a diagonal line. And so as x goes to infinity, positive or negative infinity, then the curve goes towards a line. So the curve is just following along some sort of line. Alright, so that's visually and the definition of the different types of asymptotes. Now let's figure out how to calculate these things. So first we're going to start off calculating vertical asymptotes. So a vertical asymptote occurs when a value of x is undefined at a given point. So you can see in the graph that we have there, the graph is undefined when x equals 3. So at x equals 3, the graph is undefined, and it has formed an asymptote there because the graph is never allowed to touch when x equals 3, but it has every other value. So basically at 2.999 and 3.0001, there's a value, but just not right at 3.0. So you find this point by setting the denominator of a rational function. A rational function is just a function that's like a fraction, equal to 0, since you cannot divide by 0. So the way that you get an undefined value, like we learned before, is dividing by 0. So we'll just set the denominator equal to 0. So here we solve. I'll write it on the line. When I solve for x, I get x equals 3. So the vertical asymptote is x equals 3. Since the vertical asymptote is a vertical line, the equation is always going to be x equals some constant. That's it. Let's do a little bit more challenging examples. Actually, the example is is probably the best example that I have here. If you can factor and cancel something out, so like I was able to cancel out x minus 2, then it is not an asymptote. So basically, set the denominator equal to 0 after factoring and canceling everything out. So in this case, I'll just add this note. X equals 3 is a vertical asymptote. But x equals 2 is not, because it was able to be canceled out. Okay, so that's a very important note to make. And now let's do our examples. So these examples, I see that they're not like factorable for real numbers. So these ones we're not going to factor. We're just going to say, okay, I can't factor, so I'll set the denominator equal to 0. And then solve for x. So I'll add 27 to both sides. Divide by 3 on both sides. And then take the square root. Here's the most common mistake, taking the square root of 9 and getting 3 and thinking I'm right. What mistake did I make? It's plus or minus 3. The square root of 9 can also be negative 3. So part B, again, I'm looking at that. It's not really factorable. I can't cancel anything out, so I'm just going to take the denominator and set it equal to 0. So the bottom I can factor. This will be x minus 3 times x plus 2. The numerator is not, this thing is not factorable. So that's why I said it's not factorable. Okay, so that means I have x minus 3 equals 0 and x plus 2 equals 0. So x equals 3 and x equals negative 2. These are vertical asymptotes. Okay. So that should feel a little bit familiar. Now I'm going to review the rules for calculating horizontal asymptotes, which are a little bit different. Okay. So for horizontal asymptotes, it requires you to look to determine the relationship between the leading coefficients on the numerator and denominator. And the leading coefficients are the constants in front of the term with the highest degree exponent. Okay, so top heavy means that the degree of the numerator is greater than the degree of the denominator. So looking at our example, look at the degree right here is 3 and down there is 2. So the power of the numerator is greater. This is top heavy because the top has greater power than the denominator. And so when that happens, the graph has no horizontal asymptote. So when you're top heavy, the graph has no horizontal asymptote. So looking at the graph we have, I see that there's one of those slant asymptotes right there. There is a slant asymptote, but there is no horizontal asymptote. because the function is top-heavy. So when it goes to infinity, the top of the fraction gets really, really big faster than the bottom of the function. Okay. So I just want to make note, these notes right there are the same as the previous slide. You do not have to rewrite those. So we talked about top-heavy, now let's look at balanced. So balanced means that the degree of the numerator is equal to the degree of the denominator. The horizontal asymptote is the ratio of the two leading coefficients. So I see, here's my degree. They both have a degree of 3. So I found the largest exponent in the numerator and denominator. They both have a degree of 3. So now I have to look at the leading coefficients. So here I have -2. You gotta pay attention to that negative sign. That's -2. And then what's down here? That's an invisible 1. So there is a 1 in front of that. Okay, so that means that my horizontal asymptote is the ratio of the two leading coefficients is -2 over 1, which is -2. So it's y equals -2. And you can see in my graph at -2, I do indeed have a horizontal asymptote at -2. Okay? So when they're balanced, there's equal power. So when the function goes to positive or negative infinity, they have the same amount of power, and the coefficient determines what the horizontal asymptote is. Okay? And then finally, so we've talked about top-heavy, bottom-heavy, or sorry, top-heavy, balanced. Now we have bottom-heavy. So bottom-heavy occurs when the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is 0. So looking at my degrees, I see I have a degree of 1 in the top. That's an invisible 1. And then I have a degree of 2 in the denominator. This is bottom heavy because the power in the bottom is bigger. And so that means that there's a horizontal asymptote at 0. So you can see that the function does cross right here. It crosses over, but that's okay because the functions are still getting closer and closer to that asymptote as you go to infinity. Okay? So as x goes to infinity, the bottom of the fraction gets bigger, and that's why when you have like a smaller number over a bigger number, it gets closer and closer to 0. So that's why our horizontal asymptote is at 0. Alright, so let's look at examples of that. Determine the horizontal asymptotes of the functions. So I'm going to start off each of these just by finding the powers. So in part A, I see I have a power of 1 right there. It's invisible, but it's true. And then, so I have 1 and 2 right there. So I want you to think, is this top heavy, bottom heavy, or balanced? This is bottom heavy. So the rule for bottom heavy, let's go to it. The horizontal asymptote is y equals 0. Is my horizontal asymptote. Alright. Part B, I'm going to highlight the powers. I have 2 and 2. So is this top heavy, bottom heavy, or balanced? You're right. This is balanced. So, going back to my balanced rule, what happens here when you're balanced is the horizontal asymptote is the ratio of the two leading coefficients. So I need to look at the leading coefficients. I see I have 4 and 2. So my horizontal asymptote, which I'm writing as HA, horizontal asymptote, is y equals 4 over 2, which simplifies to just 2. And then finally, C. Is C top heavy, bottom heavy, or balanced? You're right, this is top heavy. Got more excited as we went. So, the rule for top heavy is the graph has no horizontal asymptote because the top just keeps going to infinity. It doesn't go to a number. So, no horizontal asymptote. And that's it. So yeah, hopefully you learned about what asymptotes look like and how to calculate them from equations.